This entire area can be calculated from just two numbers. No thousands of rectangles, no endless addition, just the two endpoints. But how can two numbers possibly know the area of an entire curve? Let's find out. Call the accumulated area from A to this moving point x, A of x. Now move x just a tiny bit to the right. What changes? Only this thin strip of new area, and its height is approximately f of x. So the faster this boundary moves, the faster the area grows according to the height of the curve, which means a prime of x equals f of x. And that changes everything. Because if f prime of x equals f of x, then a of x and f of x have exactly the same derivative. So they can differ only by a constant. A of x equals f of x plus c. But now there's a problem. What is c? There are infinitely many shifted antiderivatives. Which one represents our actual area? Go back to the very beginning. When x equals a, the interval has zero width, so there is no accumulated area yet. A of a equals 0. Substitute x equals a. 0 equals f of a plus c. So c equals negative f of a. And now the area function becomes a of x equals f of x minus f of a. Now watch what happens when we slide the boundary all the way to b. A of b equals f of b minus f of a. And there it is, an entire continuous area reduced to two endpoint values. That is the fundamental theorem of calculus. Instead of adding infinitely many tiny pieces one by one, we find an antiderivative and evaluate it at the boundaries. For example, take f of x equals 3x squared from x equals 1 to x equals 2. An antiderivative of 3x squared is f of x equals x cubed. So the area is simply f of 2 minus f of 1. That gives 2 cubed minus 1 cubed equals 8 minus 1, which equals 7. Exact. No approximation, no thousands of rectangles, just two numbers. But now look at this. Integral of 2x cosine of x squared. Here, the antiderivative is hiding inside another function. So how do we uncover it? We reverse the chain rule. That's U-substitution. And that's the next video.